Good morning, ladies and gentlemen. Okay, this is Professor David J. De Los Reyes. Okay, the date for today is it's December 31, 2022 already. It's almost New Year. It's New Year, not yet. My topic for this morning will be a random topic, and this will be a topic on, this is a AC circuit. I will be illustrating the concept of what is so-called AC circuit for this given discussion. Okay, let's proceed. The subject matter for this morning will be uh, AC circuit, alternating current circuit. It's just a simple one. I just would like to emphasize the importance of the concepts of and how to compute for current, total impedance, true power, apparent power, and power factor for AC circuit, alternating current circuit. Okay, let's proceed. We are given a circuit here. Obviously, the circuit is an alternating current circuit. This is the symbol for alternator. It's a circle with a symbol like this symbol. It means that the power source is alternating current. The voltage is 120 volts, frequency is 60 hertz. And connected to this alternating current source, since we are on alternating current circuit, one of the configuration of the connection is actually a series. So I will be illustrating an example problem of series AC circuit for this morning. This is C1, C2, and C3, and they are all connected in series. Meaning in series, the current passing through the individual impedances are actually the same. That's the nature of series circuit. What is given is capital letter Z with the subscript 1, meaning total impedance number 1 is it is given in the so-called rectangular form. So rectangular form, there should be a real part and imaginary part. So Z1 is actually 4 plus G6 ohms, and this is with the designation I, meaning inductive. Because the sign of the imaginary part is plus, it is supposed to be inductive. Z2 is actually 5 plus J0. For the first one, for it to be inductive, the vector diagram will be like this. Okay, this is C, this is R, and this is plus Jx of L. That is for C1. For Z2, the value is actually 5 plus G0, meaning the real part is 5, the imaginary part is 0. So this is just a pure horizontal line. And R here is equal to Z, and this should be equal to 5 ohms. Okay, no vertical component, meaning Z2 is a pure resistance load. So this is with the designation PR, pure resistance. Z3, the real part is 3, the imaginary part is 4, but this is negative. So if we try to bring out the vector diagram, it should be downward. Okay, so this is minus Jx of C, this is R, and this is C total. This is C3. So this is upward for inductive, this is downward for capacitive, and this is just a pure horizontal line for a pure resistive load. So this one for a C, meaning capacitive. Pure inductive, pure resistance, and pure capacitance. 4 plus G6, this is 5 plus G0, and this is 3 minus G4. The problem is just asking, it's the basic thing, right? In the computation of the current, we needed the value of the total impedance. So the problem is asking what will be the total impedance. If we try to compress this, okay, as a single impedance, okay, what will be the value of C total equal to? Right, that's it. So after compressing it, it will now just be simply a single impedance connected to an AC source, so we could compute for the current now. The problem is asking what will be the total current. Next requirement, what will be capital letter P with the subscript T, meaning subscript T, it's the total true power. Total true power, it is actually the power consumption which we are paying to the utility companies. What will be the value of the true power? Of course, the unit of this is watts. A bigger one will be kilowatts, and a much more bigger one will be megawatts. Okay, next one. S total, capital letter S with subscript T, total apparent power. The unit of total apparent power, the importance of the apparent power is that without knowing it, we don't know the how big or how small will be the total current. So it's a must that we should know the total apparent power consumption of any given load. So the unit of total apparent power will be volt ampere. A bigger one will be a kVA, kilovolt ampere, and a bigger one will be a mega volt ampere. The last requirement is the power factor. Power factor is it's just a percentage, and the problem might be asking, is it a lagging power factor or is it a lagging or leading? So on the final answer, we will specify if the power factor will be lagging or leading. How do we know if the power factor is lagging or leading? We shall see how we will be naming our answer on the last part. Is it lagging or leading? Oh, I got my cloth eraser. So I will be erasing this one so it looks nice, right? Okay, and so with this one. The circle I've made is just to emphasize what will be the, what you call this, single equivalent. Okay. Let's try to continue. For a series circuit, whether alternating current or DC circuit, the total impedance will just be simply the summation of C1, C2, and C3. But under AC circuit, if we see summation, it should be a vectorial addition. It's not just simply the algebraic addition. Okay? So if we are adding C1, C2, and C3, we will apply our knowledge on how to add what you call this a vector quantity. Vector quantity meaning it got the real part and the imaginary part. We could not combine the real and from the imaginary. We just combine all the real parts and we just combine the imaginary parts. So the two things are actually different. So if we try to compute for C total now, it will be Z1 plus C2 plus C3. Like what I said, it should be, we will add it vectorially. So Z1 plus C2 plus C3, and luckily, the individual impedances are actually expressed in the so-called rectangular form, so there's no more problem on how to convert from polar to rectangular. They are all polar already. So if you are taking the board exams, and the given impedances are all in rectangular form, and you will there will be a time that you will be adding. Okay, amen. Because they are in rectangular form already, we are ready to add. So substituting values 4 plus J6 plus the quantity 5 plus J0 plus open quantity 3 minus J4. Like in the so-called study of AC circuit, if we try to add this, we will just add the real part first. So a 4 plus 5 plus 3, those are all real parts, right? The total sum is 12. For the imaginary part, all the values with the J sign, this is plus J6 plus J0 minus J4. So it's just like an algebra thing, right? The G terms are actually similar terms, so we could add the what do you call these coefficients like in the so-called ordinary algebra. So 6 plus 0 minus 4 will be 2, okay? But we will place the designation plus J, okay? And if we try to bring out the vector diagram of this one now, it will be the real part is 12, imaginary part is 2. So if we try to compute for the magnitude of the impedance, okay, trigonometry. You could either use Pythagoras principle or use the value or the definition of sine and cosine to get the hypotenuse. So in here, Z total will be 12.16, angle 9.46 degrees. Like when I was on the topic AC circuit, to get this angle here, we are given this side here and we are given this side. And the relationship of this side here with respect to this is tangent, right? So we'll just take the ratio 2 divided by 12. Okay? Then press second function, tangent. The angle is 9.46 degrees. Okay? Then we will take the cosine. We will take the reciprocal. We multiply that by the, what do you call this, real part, times 12. And the value will be 12.16. Okay? It is 12.16. Okay? The hypotenuse will be this 12 here divided by the cosine of 9.46. That's one solution. Second solution is we will take this value here. We will divide that by the sine of 9.46. It will still be 12.16. That's the second solution. The third solution is take the square of 12 plus the square of 2. Take the summation, then take the square root. What will come out will still be 12.16. So the value of the total impedance for the given series circuit is 12.16. The angle is 9.46 degrees. The unit is ohms. This is a unit per omega. And I place it here inductive. Inductive meaning the real part or the imaginary part rather is actually an inductance. Meaning the inductive reactance is greater. This is G6 and this is minus G4. The plus sign is bigger than the minus sign, so it should be inductive. Okay? What's next? For the total current, so it seems we are now given a power source and we are given a single impedance now. This is 120. This is C total, 12.16. Okay? And it's just a simple circuit now because we take the summation already, right? So the current will just be simply the applied voltage divided by the single equivalent of the 3 here. So it will be, I total will be the given voltage here, 120. Why I place 0 degree here? As a rule in AC circuit, the voltage, the source voltage is always the reference vector. So we place an angle for it to be 0 degree. It is at 0 degree divided by 12.16 angle 9.46 degrees. I perform the operation division here in terms of polar. So I will be knowing the angle of the current. 120 over 12.16 is 9.87 and is 0. We bring this up, negative 9.46 degree ampere. The significance of this negative sign here is lagging. Okay, so supposed to be the specification of the power factor at the last answer will be lagging. The significance of this negative sign here is lagging. So if this is the 120 angle 0, this is the current, okay? The difference in angle between this 120 volts and the current is 9.46 degrees. It's negative. So like what I said, the significance of this negative sign here is it's lagging. Okay? For the computation of the total true power, we will just use power is equal to I square R. It's the same as in DC circuit. But we will be using absolute value here. We don't include the angle, okay? That's one computation, okay? So in here, it will just be the absolute value square times R total. And the total current, the absolute value of the current is 9.87. So this is 9.87 square. R total is actually 12. This is times 12. The square of this times 12 is 1169 watts. This is actually the one we are paying to the utility companies. If you try to multiply this 1169 by how many hours you will be consuming that one, that's actually energy. And the unit of that is actually kilowatt hour. That's why our meter at the back of our house or in front of our house is actually in terms of kilowatt hour. We are charged on how much kilowatt hour we consume per month. So this is actually important to us. How about S total? S total is just actually the product of voltage and current. S is the total apparent power under AC circuit. B is the applied voltage, and I is the total current consumption. So to compute for the apparent power, it will be 120. We just use absolute value here, right? So the absolute value of 120 will be 120, and the absolute value of 9.87 is 9.87. And if we try to take the product, it's 1184. The unit is volt ampere. The unit of 120 is volt, and the unit of 9.87 is ampere. So the unit is actually volt ampere. So the total apparent power will be 1184 volt ampere. If we try to divide this by 1000, this will now be in terms of kVA. And as you can see it, the unit rating of transformers hanging on the post is always in terms of kVA. Okay? So at least you know what's the importance of apparent power. That is actually the unit kVA, the unit of the apparent power that could be carried with the transformer. It is marked on the transformer which is hanging on the post. So that is in terms of kVA, ADC. How about the power factor? Power factor, one definition, it's the ratio of true power over apparent power times 100%. We now know true power, we now know apparent power, so we will just take the ratio. 1169 divided by 1184 times 100%. It is 97.73%. And the designation should be lagging, okay, because it is inductive. Okay, so lagging, it could be a motor load maybe. Okay, or if we try to check this, one of the definition of power factor, it should be the cosine of the angle between the voltage and current. And the angle between the voltage and current is 9.46 degrees. Okay, and one of the definition of power factor is the cosine of the angle between the voltage and current. So if we try to display 9.46 here, we will take the cosine, okay, times 100%. What comes out is 98.73%. It's the same as this one. Okay, that's one definition of power factor. It is the cosine of the angle between the voltage and the current. It is still the same as 98.7%, or the other definition, it will be the ratio of the true power over apparent power times 100%. And if we try to take the ratio, it is still 98.7%. Okay, that's it, guys. This is just a good example problem for this new year here. At least we are finishing the new year with an example problem on AC circuit. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes. Okay, for those of you who will be following my channel is at www.youtube.com/@Prof. David J. De Los Reyes. If you want to watch all my videos, you could go to that link, www.youtube.com/@Prof. David J. De Los Reyes. Okay, good morning from Los Angeles. Happy New Year.